So we last time talked about molarity, and molarity is a unit of concentration, moles of solute per liter of solution. Today, let's talk about dilution. Dilution is a way to make a solution less concentrated. So this process pictured here is a dilution process. This sample is more concentrated than that sample. If I made you go through and count the little dots, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. If I counted that correctly, we got 18 dots in this beaker on the left. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 dots on the right. There's nothing that changed about the solute, because the solute's the thing present in smaller amount. There's nothing that changed about the solute as you did that dilution. The number of solute particles stayed the same. It's just distributed over a larger amount of solution now. In chemistry terms, the moles of solute in the beginning is absolutely equal to the moles of solute in the end. So if we do a little manipulation, moles initial divided by the liters initial, that would tell me the concentration of this initial solution. But if I take that moles per liter concentration and multiply it by how much solution I have, I actually get the moles of solute in the initial solution. Well, the moles of solute in the final solution is equal to the moles of solute in the initial solution. So I can think of that as being the volume in the final solution times the concentration in the final solution as well. So moles per liter, remember, that's molarity. So this relationship of moles of solute equal moles of solute initial equal to moles of solute final sets up the relationship M1 V1 is equal to M2 V2. So anytime you do a dilution problem, it holds true that moles initial is equal to moles final. And because of this relationship, you can translate it into molarity of the initial solution times the volume of the initial solution, that's this guy, is equal to molarity of the final solution times the volume of the final solution. M1 V1, M2 V2, where M1 is a molarity and M2 is a molarity. It's not moles, it's molarity. Okay, let's see it at work. How would you prepare 60 milliliters of 0.2 molar HNO3 from a stock solution of this molarity? Well, one thing we could do without even considering the dilution equation is, let me figure out how many moles of HNO3 I'm going to need in my solution that they're requesting I make. So I take my volume that I want to make in liters, 60 milliliters is 0.06 liters, and multiply it by the molarity, 0.2 molar solution is 0.2 moles in 1 liter, and I get 0.012 moles of HNO3 are required in the solution they're requesting that I make. So if I need that many moles, how much of this concentration solution am I going to need to get that many moles out of it? I can do another conversion, this many moles, HNO3, times 1 liter solution, that's an N, solution, in this 4 molar stock solution they gave me, how many liters is it going to take to get that many moles out? 0.012 divided by 4, 0.003 liters. Do a conversion, King Henry that thing if you want to, or you can do a conversion officially setting it up. That's 3 milliliters. So the way this solution would officially be prepared is I take 3 milliliters of the 4 molar solution and add it to a beaker or something. And then I add in 57 milliliters of water. So when I combine 3 milliliters of this 4 molar solution and 57 milliliters of water, what I end with is a 60 milliliter total solution that is 0.2 molar HNO3. Did I use the dilution equation in any of that? No. Could I have? Yeah. Both of those things are going in that beaker. How would I use the dilution equation? Well, let's do that next. So in my first way of approaching this problem, I started with finding the moles of this and the moles of that. But remember, the moles of solute in the beginning is equal to the moles of solute in the end when you're doing a dilution problem, and that's where this dilution equation comes from. So we can say if I start with a 4 molar solution, what volume of that am I going to need to make a 0.2 molar solution? That's 60 milliliters. And I can do 0.06 liters there. Solve that for V1. It doesn't matter if you had set it up to solve for V2. As long as the 0.2 and 0.06 go together, it doesn't matter what's what, which one's M1, which one's V1, whatever. You end up with the volume you solve for being 0.003 liters, exactly the same as we just worked it. That 0.003 liters is 3 milliliters. You're going to add 57 milliliters of water in order to end up with a 60 milliliter solution overall. Note, this M1V1 is really a ratio equation, and I did convert my volume to liters because that's what I did in the first way I worked it. However, I didn't have to do that. Because this is just a ratio, I could have said M1 times V1 is equal to M2 times V2, and I could leave my volume in milliliters. What that means then is when I solve for V1 using this ratio version, I get 3 milliliters as the final answer instead of getting liters. So because this is only a ratio equation, you can leave your volume in milliliters for this particular equation if you want to. It means that both volumes need to be in milliliters. Don't get confused and switch those back and forth. So we could do it the purple way, we could do it the orange way, we could do it the last slide, the red way. It doesn't matter, we come up with the same answer regardless. Okay, maybe that's enough of that. You get that point. Let's do another problem. A solution is prepared by dissolving this many grams of rubidium carbonate in enough water to make this solution. A 20 milliliter aliquot of this solution is then diluted. What's the concentration of rubidium in the final solution? Okay. So I need to find concentration of the initial described solution. That's where I'm going to start. I need to know the concentration of solution A. And then let's define what is an aliquot. What I'm going to do here is solution A is 0.462 grams. 462 grams, yeah, that's totally legible, in 100 milliliters. And they took a small portion of solution A and put it in along with a total volume of 400 milliliters. So a little tiny portion of solution A was transferred to a different vessel and diluted to a total volume of 400 milliliters. So they're wanting to know what's the concentration of rubidium in the solution and what's the concentration of carbonate in the solution. 232 minus. Aliquot means this small portion, the little bit of A that you took out, that you then converted into a different, bigger solution. So that's a messy but big picture view of what we've got. So we'll start with trying to determine what's the initial concentration of solution A, that thing I just erased, solution A. 0.462 grams of rubidium carbonate. RbCO3, nope, rubidium is a +1, carbonate's a -2, 2 minus. So this is a rubidium, I don't know why I've just put those parentheses, this is rubidium carbonate, Rb2CO3. I need to know that 1 mole of rubidium carbonate weighs 230.94 grams. So that would tell me moles of rubidium carbonate in my initial solution A. Do the math. Tell me what it is. I got 0.002 moles rubidium carbonate divided by 0.1 liters, because molarity is moles per liter. The concentration of rubidium carbonate in my initial solution A is 0.02 molar. Okay. 0.02 molar rubidium carbonate means my concentration of rubidium in solution A is 0.04 molar, because there are 2 rubidiums for every rubidium carbonate. Take my molarity and multiply by 2. My concentration of carbonate in my initial sample is 0.002, because there's 1 carbonate for every rubidium carbonate. Okay? This is my solution A concentration, those bottom 2 values. I'm going to have to erase some stuff so we can keep on working. Okay, so now we take out an aliquot. We've got a 100 milliliter solution that's 0.04 molar rubidium and 0.02 molar carbonate. Take out 20 milliliters of that and dilute it to a total final volume of 400 milliliters. All right, so my concentration of rubidium in the final volume of 400 milliliters is going to be equal to the concentration of rubidium right now multiplied by the tiny aliquot you took out. Okay? That results in a final rubidium concentration of 0.002 molar. And I could set up the exact same equation for carbonate, exact same but different equation for carbonate. I would plug in a different number right there. But because we recognize carbonate is half as concentrated as rubidium, always and forever, I can know that my final concentration of carbonate in my very final solution B that they're describing, and they didn't call it that, is half of rubidium, so it's 0.001. I will put in one more color up here. It would be concentration of carbonate times final volume. And I could do it in liters or milliliters, whatever. Consistency is what matters. 0.02 molar times, this is not divided by, even though it's coming underneath, times 20 milliliter aliquot. And that better come out to equal 0.001 molar. Yeah, dilutions. Almost done. A 22.02 milliliter solution with this much magnesium nitrate is mixed with this much sodium hydroxide. Calculate the concentration of ions remaining in solution after the reaction is complete. Oh, do you feel like this guy? Yeah. This is adding magnesium nitrate and sodium hydroxide. That's a sodium hydroxide. And out of that, number one, we have to come up with an equation. Okay, let them partners do-si-do get magnesium hydroxide out of it and sodium nitrate. Well, hopefully you recognize it's not balanced, so we got to work on balancing it. Okay. And then you recognize this is a precipitate. That is an insoluble salt, magnesium hydroxide. Hydroxides are insoluble with many of the things, with most of the 2 pluses. Only barium is an exception. So that's an insoluble salt. So they could have asked us, what's the limiting reactant? How much precipitate forms? But no, this time they're asking, what's the concentration of the ions in solution after the reaction is complete? Oh, brother. We are going to shortcut this and not work through the whole thing. But the way to work through the whole thing, in order to calculate the concentration of all the ions in solution after the precipitate, you really need to know who's the limiting reactant, because you're going to have some leftovers of the non-limiting reactant. But let's adjust this problem to say, calculate the concentrations of the spectator ions remaining in solution after the reaction is complete. Only the spectators. So that really means sodium and nitrate alone. So, excuse me. How do we find the concentration of nitrate in the original solution of magnesium nitrate? The concentration of nitrate is equal to 1.615 grams of magnesium nitrate. 1 mole of magnesium nitrate weighs 148.31 grams, and 1 mole of magnesium nitrate has 2 moles of nitrate. So that math will get me to moles of nitrate. I got 0.0218 moles of nitrate divided out over 0.02202 liters. 0.2202. That's 0.99, probably could round it, molar nitrate. That's just nitrate. I do the exact same thing, exact same but different thing, to calculate the concentration of sodium. This number would be 1.073 grams sodium hydroxide. This number would be the molar mass of sodium hydroxide. 23 plus 17 is 40. This would still be a 1-to-1 ratio when you're talking about solving for sodium. And then you would get moles of sodium divided by this volume in liters to get concentration of sodium. Did you follow me? Did you do it? Because you should do it. Do it. Do it, do it. So this is the concentration of nitrate in the original solution that just had magnesium nitrate. But the question is, when you combine those two things together, what happens to the volume, what happens to the concentration of nitrate? Nitrate goes from 0.99 molars distributed over a volume of 22.02 milliliters. It becomes a new concentration that is yet to be known, divided over 2202 plus 2864, divided over 50.66 milliliters. So my new concentration of nitrate is 0.43 molar. It's less than half as concentrated as it was in the beginning. This is only doing part of the problem. This is cutting out the whole bit about limiting reactant. Can you see how that snowball guy was an appropriate emotion for what you are likely feeling now? Yeah, this chapter snowballs a lot of concepts, but I got faith in you. You can do it. Let's do it.